Lesson 98, we are going to explore the normal distribution, or more commonly known as the bell curve. So here, the normal curve are defined by just two parameters, is mean, mu, and the variance, sigma squared, of the distribution. So the bell curve actually has a defined function indicated here as f of x equals to 1 over sigma square root of 2 pi times e to the power of negative x minus mu squared over 2 sigma squared, where x belongs to real function. So if you enter this equation into decimals or your calculator with particular values for sigma and mu, because those needs to be changed, then you're going to have different bell curve of different shapes or width or spread. Okay. So you can actually follow the link here in decimals to explore how changing mu and changing sigma squared can affect the shape of normal curves. Okay, so this is just an overview. Give it a try. The normal distribution. So in this lesson, we're going to explore some properties of the bell curve, commonly known as the normal distribution. It is used for continuous data like time, weight, height, IQ score. That's another very popular one. So as you saw in the exploration section, the profile of a bell curve can actually be found using a function f of x listed over here. And you only have to characterize these bell curves using two parameters, the mean and the variance, or in a sense, it's the standard deviation being the square root of variance. So the notation can be seen in the yellow box here, x being the variable, and n indicates it's a normal distribution, and the normal distribution's parameters mean goes first, comma, and then variance. The variance is sometimes listed as the square of a number commonly, and because it's easier then to tell what the standard deviation is, right? But if it's listed as a whole number, make sure you square root that number when you're picking out the standard deviation of a certain bell curve. On the right, here you have a bell curve cut into sections. So in the center, you're going to find marked 0, the mean or average of your data set. And then 1 and negative 1 here indicates the positions where you are one standard deviation from the mean of the normal distribution. And that section includes 68% of the population. No matter how thin, how narrow, how tall, how wide your bell curve is, it's always 68%. And then moving to the 2 and negative 2, that covers 95% of the population. And then from negative 3 to 3, you already cover 99.7 of the population. And this is significant because think about that, right? If your total population is 100%, probability of getting all sorts of numbers, okay, represented by your random variable x, like once you reach negative 3 and 3 standard deviations away from the mean, you're really covering everything but 0.3%. So plus or minus 3 standard deviation is often used as a benchmark to indicate any outliers. So data points that are outside of 3 or negative 3 standard deviations from the mean can be deemed as outliers. So now let us look at some properties of the normal distribution. So first of all, you should recognize that it is symmetrical about the mean mu at the center where the peak is. Since this is a probability distribution, the area under the curve must be 1. 3. The wider the curve, the larger the standard deviation sigma. Does this make sense to you? What does the standard deviation measure? Spread, right? So of course, if that number is bigger, then it will cause a bigger range or domain, put it this way, for your random variable. That means that the curve should be wider. Number 4, almost all of the data is within 3 standard deviations of the mean. As a matter of fact, that's approximately 99.7%. And then number 5, the mean is equal to the median is equal to the mode. That is, mu is equal to 1 over sigma times square root of 2 pi. And number 6, the 2 points of inflection on the curve occurs at x equals to mu plus sigma. Example 1. Air Canada hires you to redesign flight cabins. Part of the project is to develop a seat that 95% of the population can use. The mass of adults in pounds in North America are normally distributed with a mean of 145 pounds and a variance of 25 squared. 8. Draw labeled normal distribution to represent this data. So first of all, we know that the mean of the population is 145, meaning that the peak of this normal distribution of bell curve starts at 145, and then with a standard deviation of 25, you keep adding 25 to the right or subtracting 25 to the left to get the scale onto the graph. And these represents the weight or the mass of adults indicated in the question. B. Between what masses should these seats be designed for? Well, since the key here, we want 95% of the population to be able to use the seats. As a result, we know that from the notes above, this means that we are talking about 2 standard deviations away from the mean, because this will cover 95% of the population and the middle 95% of the population. Okay, so here we can say that 95% is within 2 standard deviation, and therefore the range of the mass that we should design the seats for must be 95 to 195 pounds. Okay, next, let's talk about the standard normal distribution. Z is a variable we assign to it, and it belongs to a normal distribution with a mean of 0 and 1 square as the variance. So we say that any data point on any normal distribution curve can be compared, okay? They can be compared. But let's say, like, think about 2 classes, they wrote the test, and they have different class averages, they have different standard deviations. How do I know who did better if there are 2 different tests? Then one way to compare these students is that I can translate everybody's mark onto a standard bell curve, right? And then I can compare their relative position on the standard bell curve. So this is basically the whole idea of bell curving. And the position that I was referring to is known as the Z-score, which describes how many standard deviations a person or a data point is above or below the mean. You can calculate the Z-score using the data point X minus the mean divided by sigma. Yeah, that's the standard deviation, right? So it's kind of like counting by sigma. That's what we mean by that. So when we do the translation, this way I can compare, like if somebody got a 78% on test 1, but it's a harder test, compared to someone who got an 82% on an easier test, who actually did better, right? So this way we can compare data more fairly. So next, we will be using the graphing calculator to determine the probability of different data points on a bell curve. So example 2, draw a shade graph and then determine each of the following 4 significant figures. So A, P of Z less than 0.62. So here notice how the Z-score is positive. Which side to the mean do you think it's going to rest on? Positive distance, of course, to the right. Is it going to be very far from the mean or not too far from the mean? Well, think about, the sectioning of 68%, 95%, 99.7% being 1, 2, 3 sigmas away from the mean. So 0.62 being relatively small, it's less than 1. It should be rather close. And then Z less than, meaning that we should be shading in the left side. Sorry, I'm using a mouse here. Okay, so the left side should be shaded in. All right, so we're looking for this probability. So how do I execute that on the calculator? Okay, let's see. Second function, bars. We are looking for normal CDF, which stands for a normal cumulative distribution function 2. And then the syntax here is the lower bound is basically we just need a really small number. And then the upper bound is our ending. Okay. And then mu is 0, sigma is 1. We keep that for Z. And then enter, paste. Which gives us 0.7324. Okay. Part B. This time I'm looking for P of Z greater than negative 2.1. So this time is a negative Z score. It should be on the left of the mean. And then about 2 sigma to the left. Okay, so somewhere here. The inequality that we're looking for says greater than. So we're looking at, is it a larger probability or smaller probability? Look at the area. It should be larger than what we just saw. Okay. How do we do this on the calculator? Now with the latest operating system, we go to second function vars and then normal CDF. We start from negative 2.1 according to our diagram. And then we go to a really large number. I don't know, just pick a really random large number, okay? We're using the standard normal distribution, so those stays the same. So that's roughly 0.9821, which matches the hypothesis of having a larger, okay, probability, a high probability. So the command we used is that. The command we used is that there, okay? So that shows you the boundary. You can use 1000 is big enough. All right. Now C. How about that? So probability when the Z score is between negative 0.1, so slightly to the left, to 1.3, so slightly to the right. Let's shade in this region. Now it's so convenient with the newer version of the calculators. Back in the days, the reason why it's called a CDF accumulative is you always sweep from left to right. So in order to calculate this probability, you actually had to take probability of the higher region. So let me kind of like bring you through it, right? You have to take this entire piece, okay? And then what will you do if you only want the red part? Right, you're going to subtract the probability of the smaller piece over here in order to calculate your final answer. But now with the improved technology, you don't have to do that anymore. You can really select where you want to start, the lower bound negative 0.1, and where you want to end 1.3 in your calculator. Okay, that is so much easier now. All right. Okay, here is example 3. Refer to example 1, find the probability of adults with masses below 200 pounds. So that was like the seat design question, and it's defined by 145 at the center with a standard deviation of 25. And now we want the probability of masses below 200 pounds. Let me shade in the area. Maybe this is easier. So let's say 200 is here. We're interested in this entire area. Okay, this is fun. Like that. Okay, so we want that. Well, the first method is we can compare the position of the 200 to 145 as the standard normal distribution by first calculating the Z-score. So the Z-score says 200 minus the mean 145 divided by the standard deviation 25. You get a Z-score of 2.2. And then you will calculate P of X less than or equal to 200, which is equivalent to P of Z less than or equal to 2.2, which then allows you to use your calculator just in the same way that we demonstrated in the last example, right? I can use a small number as my lower bound, and then 2.2 is what I'm interested in. And I will get 98.6% or 0.9861 if I round my answer to 4 significant figures. Okay, so that's one way of doing it. We had to do it this way in the past, but now with modern technology, you know there is a shortcut. We use a lower bound of negative 1000 to indicate, like, you know, the far end on the distribution. The upper bound, I can actually use the data 200 pounds. I can enter the actual mean of the normal distribution that I'm talking about. I can enter the standard, not the standard, but the actual standard deviation, 25. Guess what? I will get the same answer. Okay, so let me move this up. Okay, you can do that directly. All right. Next, let's look at the inverse normal distribution, which allows us to work backwards from the probability given under a bell curve to find the data point that will provide us with that particular probability. The function that we're going to use on your graphing calculator is called the inverse normal function. We will practice using that using example 4. So example 4, we're going to find a k value such that probability of z less than k is equal to 0.975. So let's indicate this on the bell curve first. Now 0.975 is a high probability, so we can imagine that we're looking at a region to the left of k that takes up most of the area under the bell curve. So I'm going to put k over here and indicate that this particular area here, okay, is 0.975. Okay, good enough. Using the calculator, I go to second distribution, so vars, and then number 3, inverse norm. The area is 0.975. And then the mean, because we're dealing with z, so this is a standard normal distribution, so we'll stick with 0 and then 1 for standard deviation. The tail part now is also new technology stuff, okay? So we are considering the region to the left of the value k, so we're going to choose left. Back then, you have no choice. Everything is always left, okay? Now, pace. This is 1.9599. All right, so the k value is approximately 1.96, okay? And we can write the probability statement as the probability of z less than 1.96 is approximately 0.975, all right? B. We have to look for the value of k such that when z is greater than k, it covers an area of 0.452. So 0.452 from the right end, so that's less than a half. So I'm going to put k somewhere on this side, knowing that the area on the right tail is 0.452. The area on the left tail must be 1 minus 0.452. So this was necessary to do the conversion if you have an older calculator that doesn't allow you to choose which tail, okay, or which side of k your area falls under, okay? And then now you can do the inverse normal. So second function vars, number 3. Now let's try both, right? So I have it on the left tail. So let's put in the area 0.548 first, the one that we have to tweak. Same mu and SD, left tail, and then let's paste this. This gives you 0.1206, okay? So about 0.121. Now, what if I try the other way? So what if I don't want to change 0.452 to 1 minus 0.452? then the area that we're talking about is to the right of the distribution, to the right of k. And this gives you the same answer. Okay, so be careful when you're using the calculator to calculate the inverse normal. Okay, make sure you know what each parameter when you enter them into the calculator mean. Okay. Next up, we have example 5. Given that x belongs to a normal distribution with a mean of 50 and variance of 9.61, find k such that p of z less than k is equal to 0.95. So how come there is an x and a z here? Well, because z in a standard normal distribution. So on the left here, we're curious to note that, well, if I translate, okay, the variable x onto a standard normal distribution, then anything less than the k value on z is going to have a probability or cover the area of 0.85. So using this sense, and then I want to map that onto the actual x distribution, okay? Then I have to kind of like, what's the relative position? I have to relate the relative position, so to speak, on both of these bell curves, meaning that I should find the z-score. So from the given, the z-score can be found using inverse normal, and then area is 0.85 on the standard normal distribution. So mu is 0, sigma is 1. To the left, everything's fine. And this is the z-score of 1.04. Okay, so let me open it here. Once I know the z-score is 1.04, I know that there's a z-score formula. So plug that in using the actual parameters in the x normal distribution. So k data point minus the mean divided by the standard deviation. So don't forget to take the square root of the variance. You plug in 104 here. Okay, so let's calculate k. I have 1.04, so I'm going to recycle this number, times the square root of 9.61, and then that's k minus 50, so plus 50. Okay, and as a result, k must equal to 53.22. Example 6. IQ scores are normally distributed with a mean of 100 and a variance of 15 squared. So here we can let x to represent IQ scores, and we can write down the notation for normal distribution with mean 100 and standard deviation 15, and then square as variance. 8. What approximate percentage of the population will have an IQ between 85 and 125? So we can write this out using a notation P of 85 less than or equal to x less than or equal to 125. Using your graphing calculator, we know that we will stick with normal CDF. And number 2 here. So lower bound is 85. And then the upper bound is 125. And then the mean is 100. And then standard deviation is 15, which gives us a probability of 0.794. Okay. Now back in the days, you have to do way more work. What you have to do first is to convert 85 into a z-score, convert 125 into a z-score, and then use just one z-score thing that you can do on the table on paper or on the calculator, and then do some subtraction. But now everything's done for you. Okay, so I'm showing it on this side just in case you're curious or you want to try it. Okay, part B. What percent will have an IQ greater than 85? So here, let's write this in a notation form. Probability of x greater than 85 is equal to question mark. So we will be using normal CDF on the calculator. This time, however, we will begin from 85 and go up, right? So let's start from a lower bound of 85 upper bound of 1000, just a really big number. This is arbitrary. And then the mean is 100 for IQ score average. And the standard deviation of this bell curve is 15. That gives us 0.8413 or 84123 significant figures. Okay, so roughly 84.1% of the population have a higher IQ than 85. Part C. What IQ corresponds to the 84th percentile? So percentile, let's recall from last year. We're considering a group of 100 people or subjects. And then the position of 84th percentile is pretty good, right? Because that means you're placed 84 in the 84th position out of 100. So 84 people below or equal to you have the same performance, so-called, all right? So in the diagram, it looks something like this. If I write it using the probability notation, I can indicate it as P of X less than question mark is equal to 0.84. So naturally, you'll be thinking, oh yeah, we have to do the inverse normal. That's right. And back in the old days, again, we don't have the option of inputting a particular mean and standard deviation into the calculator. So we had to work with z-scores first and then do the conversion later. So in this solution, that's our approach. So let's go to inverse normal. And then the area that we're talking about is 0.84. And then using a standard, so Z, I keep 0 and 1 for standard deviations and mean. We're doing the left tail, paste it. You get K equals to 0.9945, okay, as a Z-score. So now you will activate the Z-score formula so that you can translate this Z-score position to the actual IQ score bell curve using X, the data point, minus the mean over standard deviation. So times 15 and then plus 100, I get 114 or 115 if you round it, okay? So if somebody has an IQ score of 115, that means they have an IQ score higher than or equal to 84 people in a population of 100. D. In a class of 30 people, how many will have an IQ less than 70 or greater than 135? Well, here, we know that 70 and 135 are located on the bell curve in those areas. We are interested in finding the two tail ends, okay, in red. So we can calculate this probability by adding the two cases together. But alternatively, there may be a more efficient way to carry out our calculation, which is to consider the complement, right? Because in order to get the two red areas in total, all I need to do is to subtract this blue area sandwiched between the two IQ scores, okay, from the total of 100. So we can do this instead, okay? So what does that look like on the GC? So second function, distribution, number 2 for CDF. So lower end 70, upper end is 135, and then IQ score 100, mean standard deviation is 15. Okay, so let's go all the way down. And I get 0.967-ish. And then if I subtract 1 from this number, or this number, subtract from 1, I get 0.0326. We're not done yet because the question does ask how many people in a class of 30 will fall under this category. So we need to multiply our probability by 30 to get 0.977. So it's not even one person, but it's like close to one person will be either very, very, very smart with high IQ or on the lower end. Okay, so almost one person out of 30. All right.